Okay, this presentation is about sulfur, and I have identified here in this presentation sulfur as a catalyst. In biochemistry, sulfur works with warmth as a catalyst. Warmth is a catalyst, or sulfur is a catalyst, or really between the two they're catalysts. And what sulfur does is it works at the surfaces of things, the edges, the boundaries. And this is a picture here actually of sulfur that's being mined in, I think it's Saskatchewan. It's very far North America. And the way they mine this is they drill into the earth. The sulfur accumulates in deposits down below the salt deposits and below the limestone deposits in the soil. And they drill down there and they shoot superheated steam and superheated water, and they liquefy the sulfur and pump it out. It's a little bit more complex than petroleum drilling because you have to have pipes inside of pipes inside of pipes. But they pump it out into these massive football field size forms, big steel walls that they build, and they solidify it, and then they work it up with excavators. And that's elemental sulfur. It's a beautiful yellow sort of mineral thing. In agriculture, we get that's been pulverized to a powder, and we can put it in various uses, from feeding livestock to feeding soils.
Would that be sulfur smell there? Is it like active?
It doesn't really have that sulfur, that hydrogen sulfide smell of rotten eggs.
Yeah.
It doesn't have that smell. It's elemental sulfur, and so it doesn't have that acrid smell of sulfur dioxide gas. It doesn't have that rotten egg smell of hydrogen sulfide, but it's pure sulfur. And it is so versatile that it can take a valence state of anything from -2 to +6. It's a very, very versatile element in terms of its chemical reactions. It reacts a bit with just about anything. And it's a structural component of certain amino acids and vitamins, particularly the sulfur-containing amino acids of methionine and cysteine that are found in the cell walls and connective tissues of plants and animals. So it's found in the same structures in living organisms where we find the silica. So what we see in this particular plant right here, the yarrow plant, is it's got so much boundary, so much edge on its leaf that it's a very good expression of sulfur in a plant. Feathers are a good expression of sulfur in the animal kingdom. And so we see here that we see a feather, and we can see how very finely divided, what a lot of edge or surface or boundary that we have in a feather. And it's this boundary effect that give the birds such a levitational ability that they can fly. You know, it's a very remarkable thing about sulfur. So one of the things about sulfur is it's essential in making the chloroplasts that catch light in the plant kingdom. Now, it's found also in the electron transport chains of the photosynthetic process, so that it's very useful in that sequence of events that transports electrons in photosynthesis. Now, once sulfur, it's a mobile element in plants, but once it gets locked into the tissues in their molecular structure, it stays there. So when we see sulfur get into a plant, it's locking up in the same tissues where silica and boron lock up. And it stays in place once it's built in place.
So why the stag obviously being multiple horns, so is that more of a sulphur animal?
Well, in the stag, it could be moose or elk, deer. Your stag is a sort of a European version of this. Reindeer are also. You see that sulfur process in the branching, and as they're built, sulfur is active. Once those antlers are formed, it stays there. Of course, until they shed their antlers. But one of the things that's happening there is it gets built in a single year and it stays there until they're shed. So the male of these species, the Cervidaceae species, they shed their antlers once a year and they grow new ones again after that. So what we're looking at here in sulfur is we're looking at how does it act as a mineral, and we're going to also look at how it acts in plants and animals and so forth. But one of the things that sulfur is famous for is volcanic activity. Volcanoes have a history from down there in the depths of the earth that they're built up. And then when a volcanic eruption like Mount Pinatubo, when it blew up, it shot something like, I don't know, it was maybe 20, 30, 50 million tons of sulfur up into the upper atmosphere as high as 25 miles. The troposphere is only about 10 miles deep. And Pinatubo shot a great plume of volcanic ash and sulfurous gases up way above that. And this circled the earth for, it was of course precipitating out for a period of a little more than 3 years. Because sulfur has so much to do with precipitating rain, then we got in Union County, Georgia, when Pinatubo blew up, we had 24 inches of rain in the month of June. Now, the previous record occurred when Krakatoa blew up. We had 28 inches of rain recorded in Union County, Georgia. Well, in the month of July, we had 18 inches of rain. That particular year, it rained every day throughout the summer. Then in the month of August, when it looked like we might get some relief, Hurricane Hugo hit Charleston, and we got 22 inches of rain in August. We got 60 inches in 3 months, and that was more than the annual average averaged over the past 100 years. So we got more than our annual average in 3 months, and a lot of that was due to the sulfur in the atmosphere from Mount Pinatubo. Now what we see here in this middle panel is the cliffs of Dover, England, and that's gypsum. And in the mineral realm, this gypsum is a really good source for sulfur in a form that opens up the soils and unlocks the tightness and stickiness of the clays, because it not only has the sulfates, but it has a little calcium, and it exchanges that with magnesium in these tight soils. And magnesium sulfate is Epsom salts, and it's soluble and available. Now this is an acid, a sodic acid soil formation. These sorts of sulfurous soils, they're acid soils, and when they get saturated, they can slump. The soil becomes almost a fluid. And so these are some soils that can be very difficult to work with in agriculture. So we we want to look at that and think in terms of what sulfur's doing in all of these occurrences here. Sulfur is shooting up out of volcanoes. It's precipitating in these sedimentary deposits, and it can also, in the form of sulfur and soda compounds in the soil, it can make soils really rather difficult to work with. So sometimes it's good, sometimes it's not good. We've also got biological processes of sulfur, and it makes things finely divided with a lot of edge or boundary phenomena. And we see that this is a plant called goldenrod. It's actually a North American wild plant or weed. And we see that yellow sulfurous color here, but this is a plant that it really does unlock phosphorus in the soil, and it uses sulfur in that regard to do that. This is a plant that grows on acid soils. This one here, I think this is African love grass, and you see how fine it is. This is a plant that can send roots down 3 meters deep. It grows in some very, very tough conditions, and it's the source of teff, which is the staple grain of the diet in the Ethiopian highlands. And it's a very high protein grass seed. Of all of the millable grains that people eat as staple grains, this probably is the finest one. And it also leads to, in the population, people that are tall and supple, very elegant, fine-skinned, and very graceful people.
A lot of grasses that have got a more complex head, would they be similar, like sulfur?
Yeah, you're always seeing a little bit of sulfur in that complexity thing. And by having more boundaries, then it gives rise to more life forces. You're always at the boundaries. You're able to bring order out of chaos. Now, from the viewpoint of a progression of things, like Jeff was talking about out in the paddock, then sulfur plants are amongst the more important pioneers because they bring life, they bring process that builds complexity into the soil. And then better species can use that then to do things that these plants can't do. Like this plant isn't a very good plant. Once it gets up there to this stage, it isn't a very good plant for livestock to graze. You wouldn't get much production out of your dairy operation with this one, I don't think. The kinds of grasses that we're looking for in the dairy operation aren't anything like this. This one would wear your cattle's teeth out. Now, this one here, this is wild mustard. And what you see in that mustard oil that just about takes the top of your head off if you take a nip, well, mustard gas, you know, it was used as a poison gas in a couple of wars. And it's a sulfur plant that does that. And this plant actually has the sort of leaf structure and root structure and whatnot that brings sulfur into the biology of the soil. There is a sulfur cycle in the earth. And this sulfur cycle is the ocean is giving off gases rich in sulfur, and these then go through the atmosphere, they cycle through the atmosphere and nucleate rain. And it's not all volcanoes that nucleate rain, but there's a cycle of emission of sulfur off the oceans that then rains back down on the land. And that was the basis of James Lovelock's Gaia hypothesis, that the earth is a single organism and that it's alive as a single organism, and it's circulating throughout its oceans, soils, atmospheres. It's circulating this sulfur. Okay, is that yellow color associated with sulfur? And very definitely it is. And wattles are able, they're a very sulfur-rich plant. They're able to catch the sulfur and put it to work. They're able to give off root exudates that have a pH down around 3.5 or so. This is a acidity level that is capable of eating the lime components out of the rocks. So they're able to make available to themselves not just the calcium, but the magnesium in the soil. And you'd be surprised how much potassium is locked up in insoluble forms in the soil. So that plant uses sulfur to unlock these things. Yes?
So could we use a wattle, ferment the wattle, and bring sulfur back on the land?
Well, I'd say yes, you could. And if you'll look at your younger wattles, because we have wattles that are, when they first come up, they've got very, very well scalloped leaves. They're very well cut or very, very complex leaves. And then many of these wattles, once they get sort of over that young stage, then they develop very simple leaves and then they die. So once they lose that initial like complex sulfur gesture in the leaf, then they may not live just a whole lot longer.
Yeah, these
Yeah.
plants, are they plants that would need a high sulfur area, or are they plants that make available total sulfur in the soils?
Okay, good question, because if we test soils, and we'll get to that, if you test soils, you might have 5 parts per million soluble sulfur as sulfate in the soil, and you might have, depending on the soil, 200 to 500 parts per million sulfur in the total test. And these plants are plants that can access the sulfur that's there, but they also make it available to other plants. So, and they also catch sulfur that's coming through that sulfur cycle in the rainfall. One of our problems in agriculture is if we're wasting the sulfur that comes in the rainfall, then it may take a while to build that sulfur up in the soil strictly from the rainfall. And so, impatient like human beings tend to be, you know, I'd like to see it in my lifetime, then you might use something like gypsum on those soils. Or you might use elemental sulfur if they were high pH soils. So rather than have to depend on the next 200 years to get enough sulfur out of the atmosphere, we might put it on. But we'd want to put it on those plants. We'd want to ensure that we had those plants that take it up. To just add sulfur to the soil and not have the right kinds of plants doesn't really get us anywhere. One of the things about single super is it had a lot of sulfur in it. And so it caused a sort of a sulfur flush, and it made everything look really good, but it wasn't necessarily put on those things or in the right quantity to be taken up and utilized in the biology of the soil. So we want to think about that when we put inputs into agriculture. We want to put them in such a way that we hold on to them and we don't just lose them again. Now, this mineral process here also has, because sulfur is related to the edges of things, the boundaries, then it's also related to the furthest expanses of the cosmos. And what's actually happening, you remember the Olive Witcher drawings of what's happening, what's actually informing us as beings with a skin and life within us. That life is being drawn out of the cosmos, even to the furthest expanses of the cosmos. And sulfur is working in this process that the process of sulfur is streaming in from the widest expanses of the cosmos. When we thought that it was all just what goes on within, this is the sort of paradigm that we've had in our culture. We've thought that the king or the prime minister, or maybe the president, was the most important person in the country. Well, let me tell you, without the mothers in the countrysides, there's no country that would have any future or any strength. So the king is actually deriving his power from the mothers in the countryside. And not just the mothers, but the life processes that are going on in the countryside. Because if the kingdom can't support itself, then it's not going to be very powerful. And when we're looking at this in terms of drawing these energies that we're building up as vitality within our plants and animals and ourselves, then we need to have that picture in mind, that we're drawing it into us from out of the cosmos. We shouldn't really be uninformed about that. Now, in terms of testing for sulfur and putting sulfur on, the standard test that we do on soils, a Morgan extract, is really only testing the soluble sulfur. And soluble sulfur as sulfate really mechanically needs about 50 parts per million in the soil to hold the soil open mechanically, unless it's a very sandy soil. So, and if it's a very sandy soil, it may have trouble holding on to that much. But in terms of composting, in terms of mining or spreading fertilizer, then we're trying to achieve a level of 50 parts per million in that Morgan test.
So how does that relate to the Brookside test, where they're sort of saying 20, 25 parts per million?
Okay, how does that relate to, say, Brookside is setting that as a target level, and 25 parts per million? I think maybe Incitec is setting a target of 15 parts per million. Or I've seen people that had targets of 8 or 9 for pastures. And 8 or 9 for pastures, your pasture can eke by. The one we just visited after lunch probably had around 5 or below, but maybe it could have been up to 10, but it would be in that range. And I would consider that insufficient for growing good dairy pasture, and very insufficient. It certainly was insufficient on that soil to open it up. Mechanically, that soil was stuck to itself. And so the magnesium on the outer layers of the clay colloid was stuck to the magnesium on the outer layers of the next clay particle, and the whole thing was pretty much stuck together like a brick. And I would say to open that up mechanically requires about 50 parts per million. Now, that's based on my experience with soils. Brookside may think 25 is sufficient, and I've found that 25, especially the heavier the clay is, then it isn't sufficient. I wouldn't consider that a sufficient level. But that's what the lab is telling you, and they may not be varying their tests that much from the lab that I use, but they've just set that as the target.
But the test will be about the same sort of test.
Yeah, the trouble is that if you set 25 as a target, then you're going to have insufficient release of magnesium from those clay surfaces, and then you're going to have insufficient chlorophyll in the leaf, and then you're going to have insufficient photosynthesis, and then you're going to have insufficient energy for nitrogen fixation, and so it's a good tool for selling nitrogen fertilizer. So you set an insufficient target level for sulfur in the soil, and you can sell more nitrogen fertilizer, and that may be why Incitec has got 15 parts per million as their target.
Roughly 50 parts per million is for tree crops, pasture, a good average.
Yeah, it's a good average, and it's across the scale of whether the soil has a CEC of 6 or 8, or whether it has 15 or 20, or whether it has 70 or 80. It's just a target, and it doesn't tell you what the biological activity is doing, but since the biological activity is dependent upon the available surface area in the soil, and because sulfur has such an important influence on exposing the surfaces of the soil particles, then your biological activity is going to have a little more trouble if you don't have much surface area available in the soil. Now, if you cultivate and you break down all the animal tunnels and all of that sort of stuff that's going on in the soil, and you drive back and forth and compact it and everything else like that, even 50 parts per million sulfur may not be adequate.
Maybe you sulfur for like fungicide control, and if you put sulfur down, would that also have a detrimental effect of the fungi?
Okay. Well, let's look at it this way, Heinz. There's many different kinds of fungi. And what's going on in the soil with those fungi that are the best symbiotes with the plants, then they're using that sulfur and they're making silica available from the surfaces of the soil particles to the plant. Those types of microbes that are eating the plant for its silica, and they're infecting the plant, and they're just taking advantage of the plant's already developed silica. They don't like too much sulfur. They get their sulfur and their silica from the plant, and then you give them sulfur, and that chases them out of there, and it feeds the ones in the soil that you want instead. So it's not like what you're putting on to get rid of fungi in the canopy of the plant is bad for those types that are living in the soil. The ones that are eating the plant up there in the canopy are the ones that you're going to overload by giving it a little bit of sulfur in the canopy. So you're getting a different type of fungal activity. You've got in the soil, for instance, several species of trichoderma that actually eat pathogenic types of fungi in the soil. And you can dip your plants in the roots of these trichoderma species, and actually they will protect the plant's roots from the harmful types of fungi because they consume them. So it's like...
Remember we used to get tomato blight and put Epsom salts, and that's pretty much the same thing. Would it be fight fungal blight on the tomatoes?
Yeah, in the mountains of north Georgia, people would get tomato blight, and they would put Epsom salts on their garden, and it supplies enough sulfur that it would feed the right types of fungi on the soil and release more silica and make your tomatoes more immune to those blight types of fungi.
It doesn't need much, does it?
No, it doesn't need much.
It makes sulfur, not that much.
However, when you're doing total tests of the soil, they're done entirely different from the way you're doing that Morgan extract. That's for the soluble sulfates. This is for sulfur in terms of wherever it might be, however it might be in the soil. And those types of tests are done by combustion and a spectrographic analysis of the gas given off, and then you test the sulfur that way, and you may find that you have 10 times as much sulfur in the insoluble or total test of the soil, or more or less. What you're shooting for there in that analysis is you want a nitrogen to sulfur ratio in the totals of around 6 parts nitrogen to 1 part sulfur. And that pretty much gives you the available biological reserve sulfur levels that you need for good, healthy growth. It's uncommon to see that much sulfur in the total test. But then it's uncommon to see enough nitrogen in relationship to carbon in the soil either. So what we have to look at in analyzing soils is how to build our reserves so that we get the right ratios that rain or shine, and we will get the kind of nutrition, summer or winter, that grows plants as abundantly as possible.
Do the ratio for leaf as well? Do you do leaf analysis, the ratio between nitrogen and sulfur as well?
Yeah, the nitrogen to sulfur ratio in the leaf, again, is about 6 to 1. It's like the biology of the soil. But it varies for each type of plant. That's the thing. Some types of plants are real sulfur collectors, and some are not. So you've got a lot more variation in the types of plants. Now, in plant testing here, the tissue testing of plants is similar to your total acid digest of soils. So sulfur in the tissue test is also done by spectrographic analysis, where you combust a small quantity of the plant material and you run it through a spectrographic analysis. And again, there is a great deal of difference actually in plants as to how much sulfur they need. Your legumes tend to be sulfur collectors, and they'll also be richer in calcium and magnesium. So in order to get more calcium and magnesium out of the soil, then they tend to require more sulfur. Soybeans is generally got a pretty, as I recall, it's got a pretty good sulfur requirement. But having said that, there's a great deal of variation in grasses too. Now what I'm looking at here, this is a fairly good soil. I'm not sure that you can see all of the things, but I'll show you the next panel, I think. And so maybe you can read this a lot better. Sulfur down here at 27 parts per million, I consider that to be insufficient. And over here on the total test, that level of sulfur in this soil is 295 parts per million. So you can see between 27 and 295, that's a little bit more than 10 times as much in the total test. And that's not at all uncommon. And some of your plants can tap into that total test a lot better. In the leaf analysis, and the reason that I chose this particular example, the sulfur in the leaf here was, what this comes out to in percent, like 0.19%, actually comes out to be 1,900 parts per million. And this sulfur here, range that we're shooting for is between 0.2 and 0.27 27%. And nitrogen to sulfur down here in this test here was at 15 units. So what translated in this sulfur test up here, this plant probably should have been closer to 10 to 1, and it's 15 to 1. Sorry, 15 to 1 here on this one, and it was 17.6 to 1. So what you'll see a lot of times, though, in a lot of plants is you'll see much higher sulfur analyses than this. And this particular one, I don't know why it was. I know it was dairy pasture. It was one of our tests in the dairy pasture. And it may have been a dairy pasture that didn't have much clover.
The nitrogen,
Huh?
nitrogen sulfur ratio is right out there, isn't it? Not 6 to 1.
Yeah, it isn't 6 to 1 here, and the target here in this was 15 to 1. So even so, it wasn't near enough sulfur in here. It was more nitrogen. But then nitrogen could have been higher here too. So one of the things you'll see in this particular leaf test is the nitrate and ammonia were much higher than the targets. And this gives you a false nitrogen reading. So the nitrogen in this test, though it looks like it's okay, I would say the actual usable nitrogen in the leaf was more back towards the marginal side because you've got such a high level of nitrates and ammonia in the plant. In that form in the leaf, the nitrogen is not an amino acid. It's not a living component in the leaf. It's a nitrogen salt that's actually has to be digested before it's useful to the plant. In this form here, it's, I would say, toxic.
And the crude protein's not true protein then.
That's right. The crude protein in this test, where it says that the analysis was 20.5% crude protein, it's nowhere near that because the nitrogen, the form of nitrogen in the plant is not protein. So it's a concern in testing leaf and plants that if we don't test the nitrate and ammonia and we just take that spectrographic analysis for nitrogen and it says, oh, it's got this much nitrogen, and then we multiply by 6.25 to get what the crude protein is, then we're not actually finding out what the true protein level is in the plant. And an awful lot of plant analyses are done without an analysis for nitrate and ammonia, and they just test for crude protein, and it's not a measure of true protein. And if you know anything about beef or dairy or anything like that, you feed nitrates and ammonia to your cows, and what that does in terms of their weight gain, their milk production, their health in general, is you'll burn out your cows and you will actually get inferior results in weight gain and milk production. So you do want to know whether the plant is getting its nitrogen as amino acid nitrogen or whether it's getting these nitrate and ammonia salts. So I wanted to look at sulfur deficiency symptoms, and on the left here, this is tomatoes, and this is what sulfur deficiency looks like in tomatoes. This would be a tomato plant that had adequate sulfur. This is one that does not. Now, because sulfur deficiency causes magnesium deficiency, and magnesium deficiency causes deficiency in photosynthesis, and unless you're using artificial nitrogen, then it causes a nitrogen deficiency symptom, and so on and so forth. Then oftentimes sulfur deficiency is misidentified as nitrogen deficiency or magnesium deficiency, and it could be misidentified as some other deficiencies as well. This is sulfur deficiency in rice, and what we see here, what's happened in this rice field is, now this isn't the kind of rice where you flood the paddock and keep it underwater. This is the kind of rice like we're growing down the road here at Ferry Hill, that's an upland rice that's a rain-fed rice. And the the pattern of where the water has stood in the field and has drowned the soil biology and leached the sulfates. You can see that pattern in this field. Here there's adequate sulfur, adequate magnesium. Here there is not. And you'll see these sulfur deficiency symptoms in a lot of broadacre and pasture situations where you see this kind of thing like this, and you know it was caused by leaching. Well, it's sulfur leaches. It leaches rather readily. Perhaps that's one of the reasons that it's found down lower in the geological plateaus than the salt or the limestone, is because of this property that sulfates will leach, and they get down there deep enough in the earth and you get compressed, and then they get subducted when you've got subduction of continents, and they get spit out in volcanoes. So sulfur it's one of the most mobile elements in the soil, and it's very readily leachable, and this is what you see. This is sulfur deficiency in cotton. Cotton's a hibiscus. And you can see that in the older leaves, they eventually got enough sulfur and it's locked in place, and they got enough magnesium. But all of the younger growth isn't getting enough sulfur and magnesium in its early stages. And so you see how much more pale it is.
So, Hugh, is that a factor of plants picking up enough against all of them, or the plant has taken the old leaves and taken what's available for the newer leaves?
I'd say the older leaves have accumulated it. The newer leaves didn't have enough. The older leaves were still accumulating, but the newer leaves that didn't have enough may accumulate later down the track, but it's robbing the plant to have insufficient sulfur in the older leaves, and it's still migrating there. Here's sulfur deficiency in maize, and you can see how it's really resulted here in these. In maize, you see it in streaks. So right in the rib, then the sulfur is depositing in the fluid flow channel, and then out away from it, it's deficient. It just doesn't have enough to migrate to that area. So it's the same sort of thing that it's sticking where it can stick and where it's needed, but there's not enough to cover more territory than that, and you end up with those streaks. And that's classic sulfur deficiency in maize. And here you see it again. In this picture, you will also see that the surface of the soil has crusted over, and it's a tight soil. In other words, you don't have a crumbly, open surface in the soil. So it's you see the sulfur deficiency in that characteristic as well as in the foliage of the maize. Now, remedies, I don't really recommend this one. This is gypsum wallboard. I wouldn't buy gypsum wallboard just to chew it up and put it on my paddocks. I probably would use it in a limited way, but I would burn it first. I don't know what kinds of binders or, what they're using in their process, and I think I would check that out before I used any real quantity. I think I'd try to find out. They may have in old wallboard included things like asbestos and stuff in it. So I don't really know. But on a limited basis, I'd give it a go. But I don't think I would be looking for that in agriculture at large. And here's your elemental sulfur after it's been, ground up. And this would be potassium sulfate. Or I don't think it's ammonium sulfate, but in any event, you can find natural deposits of potassium sulfate, and it's also sometimes mined as potassium chloride, and through a chemical process, the sulfate is substituted for the chloride. If you're using potassium chloride, then keep in mind that the chloride is very, very salty and tends to be a soil sterilant, whereas the sulfate is something that the microbes in the soil take up very readily and they use. So if you put it on as potassium sulfate, it'll stick in the soil, even a light sandy soil, because it's taken up within the tissues of microbes and plants. But on the other hand, something like muriate of potash, potassium chloride, is not nearly so biologically friendly, and it's very, very leachable. Now, also, one of the things that we should consider, it's your soil fungi, which primarily are silica-based microbes in the soil. They're the ones that need the sulfur the most. And so if we put a fungal food, such as humic acids or humates, as compost, or if we put that fungal food in there, we will feed our sulfur inputs into the soil biology. And by putting these humic acids with the sulfur, with the gypsum or whatever, then we will hold on to our inputs. We might use a lot less sulfur in the scheme of things by incorporating it with humic acid, which is, after all, a fungal food. And I just wanted to point out here, this is a picture I took out near Gunnedah of, I was showing a farmer out there that the ants are the fungal farmers of the soil, and I stuck a shovel down in the soil in an ant heap, and I uncovered these different fungal cultures that the ants were cultivating in their ant heap. And this was massive, like fungal cultures. Ants are actually fungal farmers. They don't have to have the fungus throw up a mushroom before they can eat it. They'll bring things into their ant heap, and I think I've heard of instances where over 40 different strains of fungi were being cultivated in one ant colony. Now, of course, as I mentioned earlier, the earth has a sulfur cycle, and sulfur returns to the land in rainfall. It's being, through the life activity out here off the reef, then the sulfur is volatilized as sulfonates off of the ocean, and then it's caught up in this cloud formation that gives us rain. Plant-based remedies, like this one here, for instance, horsetail. You see how fine this is. All of your biodynamic preparation plants, this yarrow is also a biodynamic preparation plant. All of them were chosen because they have a sulfur process going on with them that's very rich or very strong. And so this is particularly rich sulfur process, but even on the other end of the scale of the biodynamic preparations, this one also has a strong sulfur process. And this one's canola, and actually canola was bred out of rape. Canola is a type of rapeseed, and rape is a plant that makes a very oily seed, and the rape was bred to canola to get rid of the racemic acids, which are rather sharp mustard type oils. But this plant is a good sulfur plant in terms of the soil, and it wakes up sulfur again in broadacre areas, so that wheat then has adequate sulfur when it follows canola. One of the things about sulfur that I failed to mention, sulfuric acid, concentrated sulfuric acid, is called oil of vitriol. And it has an oily character, and a lot of plants that make oils are using sulfur in that process. So there is something to this idea of sulfur as an oil.
So, Hugh, what about things like kale and so on from the brassica family? Are they doing something similar?
Yes, kale, I think your entire brassica family, I think more so kale than, say, cabbage. But broccoli and cauliflower and your Swedes and turnips and all those sorts of plants have a special relationship with sulfur that is very balancing with your cereal grains, oats and barley and rye and wheat and triticale and other such cereal grains. So you'll find if you plant them together as companions that they like one another. And if you want to grow the best turnips, you will plant them in with barley or oats or rye or wheat. Because what happens with the cereals is they make so much root development that they're putting sugars into the soil in the winter. They're very, very efficient photosynthesizers. If you go out in that time of year and you pinch some off and chew it, it's going to be really sweet. And so they're putting sugars into the soil that feeds nitrogen fixation. Then the protozoa in the soil eat those nitrogen-fixing microbes and release amino acid nitrogen. And then the Swedes or turnips or Chinese radishes or daikons or whatnot that are growing there will grow to large size on amino acid nitrogen. If there's any nitrates, the cereals take them up and convert them, and they don't contaminate the turnips. And then you get a turnip with the sweetest, most solid, and turnips have this really delicate, ethereal flavor that gets masked by nitrates, and you get turnips that taste bitter, then they've got nitrates in them. And you will grow far better turnips that'll get their amino acid nitrogen without nitrates if you grow them with cereals. And you can use these types of plants as parts of your cover crops or your herbal ferments or components of your composting process. I know that canola does make a very good like cover crop. I've got a different take on cover crops, I think, than what I keep hearing about. I look at growing cover crops that I harvest. But I think that the earth should always have a cover on it insofar as possible, as much of the time as possible. So I will plant cover crops, whether I harvest them or not. Like if I was growing maize, I would have a cover crop of soybeans underneath it. And I wouldn't harvest the soybeans, but they would be important to keep the earth covered and to keep things balanced. If I was growing, say, oats, I would have a cover crop of clover. This is what my grandfather, who immigrated from Sweden, did. He always sowed clover underneath his oats and had a cover crop there. But he was harvesting his oats and was, in fact, known as having some of the best oats in his district. So, yeah, I plant cover crops all the time. I would hardly imagine not planting a cover crop. In say, if I was growing wine grapes, I'd have cover crops in there. In the off-season when the vines are dormant, particularly in between, all my traffic paths and everything, I would be flavor crafting my next crop of wine by the types of plants that I planted in my cover crop. And then I'd come along and mow and mulch with those cover crop plants, keeping the soil covered all the time. I'd mow and mulch with that, and that would flavor craft my next crop of wine. So if I wanted to have a rather sharp, biting wine, I might plant mustards in it. not exactly the best prospect. Uh, but on the other hand, I might plant something sweet like barley and clover, and I might have some mild winter radishes in it, just to give it a little zing. And I might have other things, peas or lupins or things like that in it. If I wanted to get a very unusual flavor in my wine, I might put fenugreek in my winter cover crops. That might be interesting. I haven't tried that.
How about you put on like ginger or garlic? Because that doesn't get too high. The ginger garlic sits just right under the soil.
Yeah, I always mulch my ginger. I don't always mulch my garlic, and that's another story. But I have planted rocket in my ginger patch. I'll get rocket come up about halfway along, maybe after midsummer in the ginger, and then I'll be harvesting rocket before I dig my ginger. So there's a lot of things going on there that you can add, maybe companion plants or succession plants or whatever in your planting. I knew a farmer in Georgia that grew soybeans and wheat in rotation, and as the soybeans were starting to mature, he would fly on his wheat from an airplane, and the wheat would come up as the leaves were falling off the soybeans, and then he would take the headers through and harvest his soybeans, and his wheat would already be planted. And then he would harvest his wheat and no-till drill right behind it, drill his soybeans, and never lose the cover on his field. So here's some animal-based remedies. There's going to be plenty of sulfur in feathers, particularly in urine, dung, paunch manure, blood meal. All of these things contain high levels of sulfur. This is an effluent pond, for example. And we can look at these things like this is dung beetles and whatnot. This is a silky oak. These are fungi. These are plants that have a lot of sulfur processes going on with them. And your animal-based remedies here, what I'm looking at in this third slide is the pattern remedies. These are homeopathic patterns. This was a biodynamic preparation that was being made. I think, can't really tell exactly which one this was actually, but I think this one was maybe, might have been a chamomile or dandelion, but all of those had sulfur component in it. And you'd make these things up. This one you hung up in the summer sun and then buried it in the earth over the winter. And you're using this homeopathically. The sulfur processes that are at work there will be carried forward with just a spoonful in a large compost pile. Or they might get carried forward. When you're thinking substance, you're not thinking process. Let's put it that way. When you think process, then it doesn't require a lot of substance to get the process to work. There's many homeopathic formulations that don't have any of the substance left. The process has been imparted to something like water or sugar. So in terms of process remedies, there's a lot of different kinds of process remedies, and things like color and, for that matter, sound can be used to invoke certain processes. But biodynamic and homeopathic remedies I use an awful lot. These have been demonstrated to me, at least, that they're very active processes. This plant here, stinging nettle, really is one of my favorite plants to impart processes. It's got the full array of processes, very much including the sulfur. And if I took my lawnmower and harvested a couple bags of fresh chopped stinging nettles, chucked them in a 200-liter drum, and fermented them for 8 or 10 weeks, and sprayed them at 10 liters per hectare, then I would impart that process of that plant to that land. And so if any of you have large areas of something like stinging nettle or horsetail or whatever, then think about harvesting them in order to use them to make a remedy that has that process that you can impart to areas of your farm or your garden that need to have more of that process.
So that process, is that stimulating the biology to make, is that where it's aiming at?
Yeah, the process is kind of like the music at the dance, that it draws the organisms, the different types of participants, it draws them into that pattern. You can't hardly imagine having a dance that's a really like organized party without having any music. How would you do that? But the music doesn't actually have any weight. It doesn't have substance. The process is affecting the substance. You can take musical tones on a sheet that's covered with sand, and it will organize the grains of sand into patterns.
So if you wanted to do rock and roll, you put rock and roll music up. If you wanted to do the two-step, or you put those appropriate process or patterns out.
Yeah, if I wanted to get my dairy cows sort of on the edge, I might play heavy metal. But on the other hand, if I wanted to get the dairy cows to feeling really sort of like, I might play bluegrass. You know, bluegrass is a sort of an upbeat, but it's gentle, and it's you know, there's not much strain in bluegrass. Or it could be Bach or Mozart. So you can see, yep. Oh, so we're running out of time here, it looks like. There's homeopathic cell salts, and there's other sulfur remedies in the materia medica. So what I would suggest is that any sorts of our irrigation, any sorts of sprays, any sorts of dry blends, any sorts of fertilizers, we're missing an opportunity if we don't put patterns with these things, because the patterns have such an organizing influences on the substances that, and the patterns don't cost very much. If we're economical about doing it, they don't take much time. You can put the pattern on something with a homeopathic remedy, just put it in your irrigation tank, or put it in your spray tank, or just spray it over your load of fertilizer. And then when you spread it, it will have patterns with the substances.